Okay, so this is the second video about topic 6 in module 4. It's more about the percent frequency density histogram. It's based on this PowerPoint presentation. Let me just get that started. And here we go.
In a previous video, we reviewed how to make percent frequency density histograms, and we talked about the formula for percent frequency density. In this video, we want to try to address why is this a good type of histogram to make. So this is still in module 4 of the OLI textbook. That module 4 is about exploring data. Around pages 19 through 21, there's some discussion about histograms. This type of histogram is not discussed there, but it is written up in topic 6 of the workbook.
Now, as we go through the motivation for the percent frequency density histogram concept, we will discover in the process what really is the distribution of a variable. We've been using the word for a couple of weeks now, but without a very solid definition of what is a distribution of a variable. Now, it did mention that it has something to do with the shape of the number line plot or a histogram that you would get if you could collect a huge amount of data to try to find out the real truth about the population. And this is almost the right idea, but we need to make this more precise. So we want the distribution of a variable to show us what the histogram would look like if we could collect infinitely much data. And we want a function where you give it an x value, a possible value of the variable. So if you're looking at the distribution of the weights of football players, you give this function a weight, and it gives you back a measure of how popular is that weight compared with other weights. So we want to be able to use a distribution function to determine what percent of the population, maybe what percent of all the football players, have their x value, maybe their weight, in a given interval, say between 170 and 190 pounds. So what would make a really good histogram? I mean, one thing is that when you look at the bars in the histogram, the height of each bar has to really mean something. If you don't have very much data, and in a few of our examples that we made for our homework, this sort of thing, we did not have a lot of data. And so you might end up with one bar as twice as tall as the other bar, just because you've got one individual happen to be in bar A and two individuals happen to be in bar B. You see the issue. With that few individuals, maybe you just got lucky some way. Maybe next time you get a different sample and the result looks completely different. But if you have a lot of data so that each bar is representing a large number of individuals from the population, then if one bar has 50 individuals in that class and the other bar has only 25, now you think it's not just luck, there's really twice as many in the one class compared with the other. So one thing you need for a good histogram is to have many individuals belonging to each class. Some of our histograms that we've already done have not been very good for that reason. Now, it's not enough that you just have a lot of individuals in each class. You also need to have a lot of classes to make a really good histogram. Because the more classes you have, the more detail you get about the shape of the distribution. See, I have here two frequency histograms for the weights of football players. This is based on the data in the spreadsheet for the course, the tab in that spreadsheet that lists the weights of 80 football players. And I've made two histograms from that. Now, it's a little misleading because I only have 80 football players, and the graph on the right has a lot of classes, and I don't really have enough players to support all those classes. You see, the number of individuals in each class there on the right is only, I mean, the biggest ones are 8, have a frequency of 8 individuals per class, and so that's not a really great histogram, but it does show you that as you add more classes, you can get more detail about the shape, provided that you collect enough data to support it. Now, regardless what kind of histogram we're making, whether it's the frequency or the percent frequency or the percent frequency density histogram, we use Sturgis's rule to decide how many classes to use. And the nice thing about Sturgis's rule is that as the sample size grows larger, this formula for the number of classes does make the number of classes increase. So in this graph, you can see if I had a sample size of 500, I collected data for 500 individuals from a much larger population. If that was my sample size, then I would use about 10 different classes in my histogram. But if I go on up to 1,000 individuals in my sample, then I would have around 11 classes. So not only do I get more classes as the sample size grows, but I get about twice as many individuals per class for each one additional class that I add. Okay. So going from 500 to 1,000 individuals only added one class, so I have a lot more individuals in each class. So Sturgis's rule is helping us to achieve both goals, having a lot of classes and a lot of individuals per class at the same time. Now, any other function that bends downwards like this, like the square root, for example, it would also have the same effect. Sturgis had some reasons from information theory why he thought you could get more information out of your graph if you go with a logarithmic rule like this. But all of this should be regarded as Sturgis's suggestion rather than Sturgis's rule, because many schemes could achieve the basic purpose just as well. But Sturgis's rule does not solve all of our problems about trying to make the perfect histogram. So, 3 kinds of graph that we've learned about. Even if you use Sturgis's rule, they do not approach the perfect histogram. The number line plot and the frequency histogram just get taller as you collect more data. The number of individuals in each class is growing, and that makes the graph just keep getting taller. It does not approach any particular curve. On the other hand, the frequency histogram tends to flatten out like a pancake as you collect more data. I'll show you with pictures in the following slides why the frequency histogram, the percent frequency histogram, and the number line plot all fail to do the right thing. The one that does work out right is the percent frequency density histogram. And I have a couple of slides to show you how that happens. So what would happen to a number line plot if you could collect a huge amount of data? So here's a number line plot that we made for the distribution of the diameter of the oak trees. And it's not a real impressive number line plot because we did not collect a whole lot of data. If we collected more data, we might think that now we're beginning to see the shape of the distribution. So what we want is a function where you give it an x value, and then how tall that function is tells you relatively how popular is that particular value of x. So after collecting some more data, now we might think, okay, if we could make a formula for this curve, that would be the distribution of the variable. The problem is, whatever we come up with, whatever formula we make, it's not going to be right, because if we collect even more data, the whole thing will just get taller, and it's not going to approach any curve that we could draw. So a number line plot does not approach the true distribution, or does not approach anything as you collect more and more data. You just keep getting new functions like the blue one or the green one higher up the page as you go. It just gets taller. Frequency histograms have the same problem as the number line plot. Sturgis's rule will make you add more classes, but the number of individuals in each class grows faster, so the thing just keeps getting taller. The percent frequency histogram has the opposite problem. As you add more data, you add more classes. But all those percentages, the heights of the bars, have to add up to 100%. Get more and more bars, the percent of the individuals belonging to each bar must be falling. And so if you imagine by the time you get to 1,000 different classes, 1,000 bars in your histogram, what percent of the individuals belong to each one? Well, on average, less than 1%. So this histogram gets shorter as you add more data. Now, what happens to a percent frequency density histogram is just the right thing. It just gets smoother. Because in this type of histogram, we set it up so that the area of each bar is just the percent. So on the vertical axis, we have so many percent per pound. On the horizontal axis, we have so many pounds. If you wanted to get the area of one of these little rectangles on the graph paper, the width is in pounds, the height is in percent per pound. You multiply, the pounds cancel out. Each little square on the graph paper is some number of percents. And the total is 100%. So as you collect more data, that total area stays fixed. So the thing is not getting taller or shorter. It's like a water balloon. You squeeze it one place, it's got to pop out somewhere else. But as you get more and more classes, the envelope on top of this histogram becomes smoother and smoother. And it'll approach some kind of a curve. If you could find a formula for that curve, then that would be the true distribution of the variable. Now, in statistics, we never really find out the true distribution. We use statistics when we're studying a large population that's so large, we cannot get information about every individual. To get a perfectly smooth curve, we would need infinitely much data, which we cannot get. So our data produces chunky histograms, but maybe some kind of probability theory might give us a smooth curve that we think this histogram should approach. And part of the job of statistics is to measure the goodness of fit to compare the theoretical curve, which is the smooth blue curve in the right-hand diagram here, against a chunky histogram made from data. All right, so that's it for this presentation, and I'll see you next time.